Welcome everyone. This presentation is all about table interpretation in section 1 of UMAT. Now you can see we're at this point now, tutorial 7, table interpretation. It's one of the two videos I've got under the data interpretation set, the other being the graph interpretation, which we'll get to next. So we'll do some table interpretation in a minute. Just first a few basic tips. The first and most important is just to be sure that you really understand what the table is showing before you begin to jump into the answers and rule them in or out. So usually interpreting a table isn't the most difficult thing, but in UMAT there's often some trick or a few tricks with the way the data is presented. So it's really important to be careful in reading the headings, the subheadings, the units in particular. Often there's some little trick in the way the units are presented. So really make sure you understand what the table is showing before you go into your working. The second point there is saying be careful with the finer points of the way the multiple choice answers are phrased. Often with these questions I tell students to get their lawyer hat on. You really need to think kind of like a lawyer here and be critical of every single word and the way things are phrased. So for example, if a table is showing you data about Australia and it says in Australia, then you really ideally would have a multiple choice answer which also says in Australia. Because if it doesn't have that, it implies that it could be in the world or something else. It's that kind of finer point reading where you're picking up on all the details and making sure they match with the data set. That's very important here. Third point, also very important. This is one of the key things that they play on with data questions. It's the difference between, on the one hand, rate or proportional percentage, which for our present purpose is all the same thing basically. And on the other hand, number or just the raw amount of something. So again, just as an example, if you have a table showing the rates of smoking, say, in Australia versus India, well, the rate of smoking might be a lot lower in India, but if an answer says that there are less people in India who smoke, that would be incorrect because the table is dealing with the rate or proportion, whereas the answer in that case, or in that example, is dealing with the raw number. So it's a very important difference to pick up on. And this final point here is just saying only make conclusions that are within the scope of the data provided. So often you'll see answers which, as it says here, go into why a certain data trend occurred or make predictions about the future, but generally they're incorrect because you can't really make assumptions about why these things happened or what will happen in the future. So just keep your answers to what you know for sure. With that said, let's go to the first question now. So how do we begin a question like this? There's two approaches. One is to begin by having a look at the data and just get a feel for how it's all presented and what it's saying. And once you've done that, then going to the question and then evaluating the answers. So going from top to bottom, basically. That's what I tend to do. The other approach is to begin by reading the question and using that question to guide the parts of the table that you really need to focus on. So it's a more targeted approach. I think to some extent it depends too on how specific the question is. So if you have a very general question like this, it's very difficult to focus in on any one part of the table. It doesn't really give you any guidance as to what you need to work out. Whereas if this question is something specific like in which year was dementia the third highest cause of death in Australia, then you would know exactly which part of the table to look at and you could get to the answer more quickly. But given that's not the case for this one, I'm going to begin by having a look at the table just to kick things off. I start by looking at the title, so leading causes of death Australia in selected years, and they're given there. So already we've got a lot of information. We're dealing with causes of death just in Australia, not any broader than that, and only in these 3 years, which you can see are about 4 to 5 years spaced apart. If we go down now to the subheadings, we've got the causes of death down here. We've got 10 of them. And then we've got the 3 years mentioned above, 06, 10 and 15. And for each of those 3 years there are 2 columns. One shows the number, which presumably based on the title is the number of deaths in Australia in that year caused by each of these conditions. The other column is the rank. So the rank presumably is just ranking those numbers from 1 through to whatever the bottom is. I guess the other trick here is to pick up on the fact that the 10 conditions picked here and the ranking that they were put in is based on the 2015 column. You can see 2015, the columns go from the highest number to the lowest, or in other words, would rank 1 through to 10 in perfect order. So really, the conditions here and the order they're put in is based on the 2015 columns, and the other two you can see are a bit jumbled up because obviously the conditions were in a different order in that particular year. The only other column of interest is this final one, which is showing the median age of death from each of the conditions we can't be sure. We can be sure. It's in 2015. So for each of the 10 conditions, this is the median age of death from that condition in 2015. So if we go to the question now, which of the following can be concluded? We'll look at option A to begin with. I think in many ways it's quite a good answer. You can see that the wording is pretty similar to the data. We're dealing with the annual number of deaths, which is what the table is showing. It's dealing with the raw number. Chronic lower respiratory diseases, again, that's word for word what they have in the table. And it mentions in Australia, which is what we're dealing with again from the table. So a lot of it is very well worded. The big red flag though here is that it's asking you to make a prediction about what will happen in the future, and we just can't do that. It may be very tempting. You can see that it's probably going to be true because if we track through the chronic lower respiratory disease line or row, 5,500, then 6,000, then 8, or basically 8,000. In another 5 years with that upsloping trend, you would imagine that the number would be over 8,000, but you just can't be sure. If there is, for example, a new treatment option that becomes available in that time, or if the population decreases in that time, then it might not be the case. So even though option A may look quite good, remember anything about making predictions about the future is almost always wrong. Option B, again, it looks quite good. A lot of the wording is quite good. You can see we're dealing with in Australia in 2015, which is again in the table, and it's referring to dementia, including Alzheimer's, which again is the wording used here. So a lot of it's quite good. But there are two main problems with option B. One is that it's dealing with the average age of death, whereas up here we can see the data set is dealing with the median age. So even though they're quite similar, they are different concepts, and so you can't conclude that. The other problem is that the answer is implying that the condition with the highest average age of death in Australia was dementia overall, out of all the conditions that leads to death, whereas this table is just showing the top 10. So it may be that below the top 10, the 15th or 20th ranked condition has a higher median age of death than dementia at 88.6. It may have a median age of 90, say, and we just can't see it because at the moment we're dealing with just the top 10. But given this answer doesn't mention just the top 10, it's referring to all causes of death. That's the other reason that we can't conclude B. Option C, in 2006, the top 10 leading causes of death in Australia were not the same as those in 2015. So it sounds pretty good. You can see we've got both 2006 and 2015 in the table. Now, the way to work out whether this is the case, we know that in 2015, the top 10 causes of death were the ones shown, because we can see here 1 through to 10. So these are the top 10 causes of death in 2015. The way to work out if they were or weren't the case in 2006 is look at the rank column here for 06. We can see they're mostly in the top 10, but there is one number here, which is 11. So heart failure was ranked 11th in 06. And therefore, some other condition which we can't see would have been ranked 10th in 2006. So in other words, in 2006, some other condition apart from heart failure would have been in the top 10 instead of heart failure. And therefore, option C is true. In 2006, the top 10 causes of death would have been different. And again, you can see the wording in that answer is very good. It's the same as the data set. So C is correct. D, the problem there is, again, it's asking you to identify a reason why a trend in the data is occurring. So it's saying that dementia has gone up from rank 4 to 3 to 2, so it's trending upwards quite sharply. And look, it may very well be, or it almost certainly is, at least in part due to the aging population. But there may be other factors at play, or that may even not be a factor of itself. You just can't make any kind of assumption or prediction about why things are occurring. So that's why option D would be wrong. Question 2 now. It's the same table, and almost the same question. The only slight difference is now the question includes about causes of death in Australia. So you don't need to be quite as pedantic about finding the words causes of death or in Australia in your answers because they're already given to you in the question. Apart from that, it's the same process for solving it. We go through the answers one by one and just see which is the best of the four. So option A. Now option A may look pretty tempting because you can see that ischemic heart disease is coming down in terms of raw number over time, whereas dementia is going up. And so it may look as though within, say, 10 years, dementia may overtake ischemic heart disease. But unfortunately, the red flag that should be jumping out at you for this answer is the fact that you cannot make predictions about the future. Because for all we know, there may be a new preventative or treatment option that comes up for one of the diseases which alters the course of the numbers or alters the trends. And just as a principle in UMAT, you really shouldn't be making predictions about the future. So that's why option A is wrong. It's particularly true for this answer, given it's so definitely worded. It's saying dementia will overtake. Not that it may overtake or it could overtake, it's saying it will, which is very definite. And when you get a definite answer like that, you need to be very sure that it's correct before you go for it. So that's why A is wrong. The other issue with A, just quickly, is that foreseeable future is a very vague term. You could define that in a number of different ways. So those are the concerns with option A. With B may be tempting given that out of trachea, bronchus, and lung cancer and cerebrovascular diseases, which are found up here in the table, out of those two, it's the trachea, bronchus, and lung cancer that seems to strike people at a younger age, at 73.5, or the median at 73.5. And that is, of course, keeping with our answer here of someone who is 73 years old. So you may think that that match may be enough to go for B. But there are a number of reasons why you can't really conclude this. One is that the frequency of trachea, bronchus, and lung cancer versus cerebrovascular diseases is different. And not only is it different, but the trachea, bronchus, and lung cancer occurs less often. So even if the median age is more in keeping with what we're looking for, it does still happen less overall, and you can't make a prediction about whether those two sort of cancel out or override each other. You just don't have that information. The other issue is, for all we know, say with trachea, bronchus, and lung cancer, there may be what's called a bimodal age distribution, where it strikes people at a young age, but also an old age. So it might strike people at, say, 30 to 40 years old, quite a lot, and then dip and then reoccur at about 90 to 100, for all we know. And if that's the case, then even though the median age is 73.5, it might not strike a lot of people in their 70s. So we just don't know enough information about the distribution as well. And for those reasons, B is not the best answer. Option C looks pretty straightforward. The issue there is that given the question is framed as causes of death in Australia, and I'm talking about the rate of death, then we're really talking about the rate of death in Australia over this time period. And unfortunately, the table deals with raw numbers, not rate. So it comes back to that idea of there is a difference between, on the one hand, raw numbers, and on the other, proportion or rate or percentage. So the reason why this is wrong, in other words, is even though the number of people affected by dementia or dying of dementia over this period is increasing, as we can see from 6,000 up to 12,000, if the population of Australia as a whole increased at an even faster rate than that, if it, say, doubled between 06 and 10, and then again doubled between 2010 and 15, then the rate as a proportion of the whole population would actually be going down. And we just can't conclude that. We don't know whether that's true or not. That's why option C is also wrong. With D, again, you can see it's very well worded. In each of the 3 years, the number of people who died, which is good. So we've got the 3 years that we have in the table in the answer as well. It's dealing with the number of people, which is what the table is showing. It's dealing with ischemic heart disease, which is given up at the top here in the table. And it's saying approximately, so it's nice and general. It's saying about, not exactly, just about. It's approximately double the number who died from cerebrovascular diseases. So if we go through the 3 years and check, you can see 23,000 and then 11,500, 21,000 and about 11,000 there, and then just below 20,000 and 10,000 there. So not perfect, but it's pretty close to being double. So, and again, it comes back to how good or bad are the remaining options. And we've gone through the first three options and said that none of them are really particularly good. So given that, and given the wording of this is very good, both in terms of all the details being there, but also being quite general, by saying approximately, option D would be the best answer out of those four. So that'd be the correct answer. New question now, and it comes with a new table, and this one's a little bit more difficult than the last one, so we'll take a few minutes to go through it. You can see here at the top that this is the estimated resident population of Southeast Queensland over a 10-year period from June 2003 to 13. There's a lot going on and there's a lot of different sections. I'm going to start kind of on the left and work my way over gradually to the right. And I think just to illustrate, first things first, we can see here on the left that each row represents a different part of Southeast Queensland. It probably helps if you know a bit about the geography of Southeast Queensland. So in the real UMAT exam, they wouldn't do that to you. They wouldn't make a question which is based partly on knowledge. But I'll let you know now that these areas shown on the left are all a part of Southeast Queensland, which is why that number at the top, or indeed all of those numbers at the top, are just the sum of all the numbers beneath them in each column, because all of these add up to give the total for Southeast Queensland. What I'm going to do is pick one of these areas, say Brisbane East, and I'm going to go across the row and just explain what each number, or at least each section, means in terms of the overall table. So with Brisbane East, let's just focus on this first sort of box here. You can see that we've got a box here. Now it's referring to the estimated resident population at 30th of June over various years in this 10-year period, and it's in terms of the number. So we're using raw number of people in this section. So in other words, this number here, 185,000 effectively, is the population in terms of the raw number of people in Brisbane East in 2003. That's all it's saying. And you can see that the population in Brisbane East then increases over the years. 2008, 5 years later, it's increased by about 22,000, 23,000. And then it keeps going up and up over 2012 and 13. So that's just the raw number of people, and it's showing the increase over time. Now, the second part of the table, this kind of box here, if we keep looking at Brisbane East, we can see that we have a number here, 4,068. So what does that mean? Well, look at the section above. We're looking at the average annual growth in terms of number. So we're still looking at the number of people. We're still got the same units as before, but we're now looking at the average annual growth. So they're saying that the number of people that the population increases by in Brisbane East every year is about 4,068. I think the trap with this particular column and this particular number is thinking that that represents the total growth over the whole 10-year period. In other words, you're thinking that this 4,000 means that the population of Brisbane East increased by only 4,000 over that 10-year period. But as you can see, it actually increased by about 40,000. And that's because this is just the increase in any one given year on average, not the whole 10-year period. So you have to times that by 10 to give the overall increase, which is shown here between 185,000 and 225,000. If you look at the next column, this number here, 3,708. So you can see that this is, again, same thing. It's the average annual growth in terms of raw number of people, but we're now looking at just the 08 to the 13 period, which is the latter half of the 10-year period. It's the latter 5 years of that 10-year period. So in terms of how to interpret this, if you were required to interpret it, the fact that that number is a bit lower than the overall growth for the 10-year period suggests that the rate of growth has decreased. So there are still more people moving, or the population of Brisbane East rather is still increasing. It's just not increasing quite as rapidly as before, because this column here, which focuses on just the latter half, we can see is already less than the first column here. So the average for each year in that latter half is 3,700, whereas for the whole 10-year period it was 4,000. So there was more growth in the first half than the second half, is what that's showing basically. It's similar if we go to the next column where we see the 3,167. So again, it's a smaller number, and if you look up above that, you can see that the time period here is just the final year of that 10-year period. So in that final year, there was only a growth of 3,100, which is again a lot less than both the latter 5 years and the total for the 10-year period. So again, it suggests that the growth, while the population is still growing, the number of people by which it's increasing has gone down over the years. That's the way to interpret that. So it's still increasing, but increasing at a decreasing rate. If we go to the final column, you can see that the topic at the top, average annual growth, is the same as it is here, but now the units have changed. Whereas we had numbers before, and we were dealing in just the raw number of people, in this column we're dealing with the percentage change. So the percentage is just based on the numbers here as a function of the population in total. So obviously, it's dependent on how big the population is. You can see that the Gold Coast, in terms of raw numbers, had the biggest growth over all 3 years, or sorry, over all 10 years. But it also had the largest population the whole way through. So proportionally, its growth is actually very similar to the smaller centres, which had a smaller initial population, but also a smaller growth in terms of raw numbers. It's that idea of a proportional increase being shown here in the final section. And again, you can see that, say, in Brisbane East, the average annual growth has decreased as we start to focus more and more on the latter half and in the final year of that 10-year period. So it's saying that the growth of the population is still increasing over time. It's just increasing less and less. So with all that in mind, let's look at the question and then the answers. So which of the following can be concluded? Option A, there were approximately 1.3 million people living in parts of Queensland other than the southeast in 2008. So the first step to working out if this is correct is appreciating that the total population for southeast Queensland is shown here, and given we're looking at 2008, the number we want here is 2.9 million. And then we just have to understand that to work out the population who are living in Queensland but not in southeast Queensland is simply the difference between this number at the top and the number here at the bottom in the same year, which is the total for all of Queensland. So that is the difference between these two. And that number, I would say, is pretty close to 1.3 million. We've got 2.9 and then 4.2 million. So it's about 1.3, the difference. So option A is looking pretty good. With these ones, unless you're definitely sure, it's always good to go through the other options just to see if there's one which is even better or more definite. So option B, the greatest annual population growth in terms of percentage. So we're looking at this final box now because that's the one with the average growth in terms of percent. The greatest annual population growth in Queensland between 03 and 13. So now we're just looking at this column here because that's the right time period. Occurred on the Gold Coast. So if we look down this column, the biggest number I can see is actually here for Moreton Bay South, whereas the Gold Coast is a bit less at 2.7. So that suggests that option B is not correct. I think the reason for option B, the reason why they put it in there, is because in terms of real raw numbers, the Gold Coast did increase the most, but proportionally, or as a percentage, it wasn't the highest because it had a very big population to begin with, as per what I was mentioning before. So that's the trap there, and that's why some people might go for option B, but in this case it's not correct. Option C, the red flag there I guess is just that, again, you're being asked to make a prediction about the future, so don't do that. Even if it looks tempting, you can't say with any certainty that the population will go past 1 million in 2013. And just finally, option D, the rate of population growth in Queensland increased throughout the 03 to 13 period. So we're looking at Queensland as a whole, which is that final row. We're looking at the rate of population growth. So that's the numbers down here in that final section. Now, while the population did grow, we're looking at the rate that it grew. In other words, is it an upsloping curve or is it more of a downsloping curve? And I would say that given over the whole period the growth was 2.2%, and then over the latter half it was just 2%, and then the last year was 1.9%, that growth rate is decreasing. So again, even though the growth is still occurring, even though the population is going up, it's going up at a decreasing rate. And so that's why option D would be wrong, because the rate of population growth is actually going down. And so out of all those options, I think the best is still option A, which is why it would be the correct answer. On to question 4 now, which I think is a little bit simpler. Again, just begin by looking at the title of the graph and working your way down systematically. So we're now looking at apple production in Australia. And we can see here at the top there are 3 years in a row of 04, 05, and 06. And we can assume that they represent each of the 3 columns we've got in the table. Moving down again, this line here is referring to the number of trees. The only trick there is that we've got this in brackets, 0, 0, 0. So what this means is every number you see, you have to add another 3 zeros onto the end of it. So for example, in 2004, the total number of trees would have been 10 million rather than 10,000. That's the only trap there. Moving down again, you can see that this part here, which is the bulk of the table, is showing the production of fruit in terms of fresh weight. And again, we have to add the 3 zeros onto the end of it. And the T there is the unit, so that's tons. So for example, in 2004, there would have been 3,200 tons of the bonds of fruit produced. And that's how you read this bulk part of the table. It's just year by year and type by type in terms of fruit. This line here, total production, we can assume from a rough addition of all the numbers above it is just the total of each of these numbers for a given year. And I think the only slightly tricky thing here is that bottom line, yield, kilogram per tree. So just take a moment to think about what this means. It's saying how many kilograms of fruit was yielded per tree. So it's a function of both the total amount of fruit and the number of trees. Now we have the total amount of fruit in terms of weight. That's what the main part of the table here is all about. But nowhere does it give us anything about the number of trees that it was required to produce that amount. So that's just something to keep in mind, that bottom line, that's referring to yield per tree, and we don't really know the number of trees at that point, or at this point. Let's go on to the question. So which of the following can't reasonably be concluded? Again, this is just a trick they throw in all throughout the paper, all sections, or mainly sections 1 and 2. That word can't, very easy to skim over it, but we're looking for which of the following can't be concluded. So option A, the highest overall yield of the years shown occurred in 2005. That looks pretty good to me. Again, you can see that the wording of it, overall yield kilogram per tree, which is pretty much what they've got down here, of the years shown, which is good because it's saying that we're just interested in 3 years shown here, not all of the years in history. And of those 3 years, the highest number was in 05. And as you can see, that is the case here, because 35 is more than these two. So A is looking pretty good. But remember, look for the one that can't be concluded. So therefore, A can't be the correct answer. Option B, approximately 320,000 kilograms of fruit was produced from the tree shown in the table in 2006. So, where do we need to look to find out if this is accurate? Well, the line that shows the total production in terms of fresh weight is this one here. And we can see that this option is saying that approximately 320,000 kilograms are produced in 06. As we can see here though, going down 06, that seems to be pretty inaccurate because we've only got 276 there. So at this stage, that's probably the correct answer because it's the one which is incorrect based on the question. Okay, we'll keep going. Option C, 3,200 tons of bonds of fruit were produced in 2004 in Australia. Again, that's pretty straightforward. That's the one we're looking at before. So 3,200 in Australia, bonds of fruit. It's all in the table there. So that answer would be accurate, which means it's incorrect. And final option, production of Bonza apples decreased between each of the years shown in the table. Again, it's pretty well worded. You can see Bonza apples, so they're specifying a particular row, and a decrease between each of the years shown in the table. So again, it's referring just to the years shown in the table, which is good. And we can see that it does go down from 3.2 to 2.8 to 2.1. So D is also accurate, which means it is also wrong. So we can see that A, C, and D are all true statements, which means that B must be the correct answer. We'll go now to question 5. It's the same table, but the new question is which type of tree provided the greatest yield in terms of kilograms per tree in 2006? So this goes back to what I was mentioning a minute ago about how the final line there, yield kilograms per tree, which after all is what we're interested in, is a bit tricky and a bit difficult to deduce because if you think about what it means, it's talking about how much each type of tree, in other words, each type of these different varieties of trees produced on average. Now that requires both the knowledge of how much total fruit those trees produced, and we have that. That's what this main part of the table here is all about. But it also requires us to know how many trees of each different type there were to make that amount of fruit, because it's about yield kilograms per tree. You have to know how many trees were involved. And so the answer, I'll give it away at this point, is D. You just can't conclude it from the data because we don't have enough data or any data about the number of trees for each of the different fruit varieties. So that's why the answer is D. You may be tempted to go for, say, Granny Smith, because you can see here that Granny Smith produced the most in 2006 in terms of the raw number. But for all we know, Granny Smith may have also had the greatest number of trees to produce that fruit. And in the end, we're interested in the yield in terms of kilograms per tree. So you have to take the total amount in kilograms and divide it by the total number of trees, which we don't have. So the answer is D. Next question now. As always, begin by reading the title. So we're now looking at the purchase of medications in Mexico as broken down by various demographic and socioeconomic characteristics in 98 and 99, as we've got here. So it's quite a big table and there's quite a lot going on. And there's a couple of terms you might not be familiar with, namely the prevalence ratio here and the confidence interval. I'll go through and explain what they are in a minute, but in the real UMAT exam, I think if they were to give you terms like that, they'd be very careful to provide an explanation. But it's still good to know what they are beforehand because it's just a lot quicker if you are already familiar with the concept before the exam. Now, in terms of the table, just to begin with, like I said before, there's a lot going on. I think it makes it a bit clearer if I break it down into a few different compartments. So I'm just going to grab the pen and break it into three parts. So one line down here and another down there. Now, if we begin with the compartment on the left-hand side, so just here, I think it's pretty clear. What we've got here are various demographic groups, so age, gender, education, etc. And under each of those, we have the various subgroups in terms of age, gender, etc. So that's pretty straightforward, and we can see that every row has a certain set of numbers, which we'll go through in a minute and clarify. So that's all that's happening down the left-hand side. It's just the various demographic groups, which are here on the far left, and then under those, indented a bit, we've got the various subgroups. Now, if we look at the second category, which is in the middle of the table, there's quite a few numbers going on. We can see in every row we've got three numbers, a number here, then one in brackets, and then another one on the right-hand side. So how do we interpret what these mean? I'm going to begin by just explaining that the total number of people in this study is 770. So I'm going to write that there because it's a pretty important bit of information. And I think it helps to clarify what's going on here. So I've got 770 people in the study as a whole. Now, if we go through these numbers in the table, you can see that in every demographic group, say age to begin with, the numbers here add up to give about 770. Likewise with gender, the two numbers here are again about 770. And it's the same as you go down, they're all 770. So what this is showing you is that there are 770 people in the study as a whole, and obviously that number breaks down in various ways by age and gender and education. And that's what we've got here on the left-hand side. So these are the age groups in terms of the number of people in each age group out of this total of 770 people. That's all that these numbers are showing. Now, the numbers on the left-hand side here under the prevalence column, or given it says here prevalence, we can assume that both the number here on the left-hand side and the one next to it, which is inside the brackets, both refer to the prevalence in terms of purchase of medications. That's what the subtitles we have here show. So what that means is the number here is the raw number of people who are purchasing medications in Mexico, And the number in brackets, as we can see up here, is the percentage. So in other words, let's just pick out a particular row just to illustrate. So what we're saying is, in this row here, out of the 770 people who are in the study in total, there are 203 people who are aged between 18 and 34. And of those 203 people, 51 of them have purchased medications, and that equates to 20.2% of that total subgroup of 203 people. Now, you might pick up on the fact that that's not quite right, that 51 out of 203 isn't quite 20%, it's a bit more, but it just comes back to a technicality we've got down here. If you see the subnote C, percentages are weighted for the probability of selection and so on. So it's just a technical point there as to why the numbers don't quite fit, but basically it's referring to the prevalence of purchasing medications in that subgroup out of the subtotal. Likewise, if you go to the next, or if you go to a different category even, let's go to gender. So out of the 770 people in the study in total, there were 308 men, and of those, 66 purchased medications, which equates to about 20.7%. That's the way to interpret the numbers here in this second column, or in this second category, I'll say. Now, if we go to the final section here on the right-hand side, we're dealing now with the two concepts I mentioned before, the prevalence ratio and the confidence interval. The prevalence ratio is just a function of how likely a certain group is to experience a certain outcome relative to another group. So if a person from group A is twice as likely to suffer from a certain disease, say, than a person taken from group B, then the prevalence ratio of the disease in group A is 2, because they're twice as likely to develop it. If it was 3 times more likely, then the prevalence ratio would be 3. So it's fairly straightforward. If it's below 1, as we've got here with 0.9, that means that that group is less likely than the reference group to experience that particular outcome. So 1 means it's the same likelihood. Anything below 1 means you're less likely. Anything above 1 means you're more likely. So that begs the question, well, what's the reference group here? If we're saying that this particular group at the top, the 18 to 34-year-olds, had a prevalence ratio of 1.1, what is that relative to? Because it's a relative, it's a ratio, so it's a relative figure. Well, as you can see here, we've got a reference group in each of the demographic categories. So in each of the demographic categories, one subgroup, so in terms of age, it was the 55 plus group, are chosen to be the reference group. And the other scores are based on that reference group. So prevalence ratio of 1.1 means that in this study, people who are between 18 and 34 are 1.1 times more likely to purchase medications than people who are in the reference group, which is 55 plus. That's how we interpret the prevalence ratio. Now, the confidence interval is related to the prevalence ratio, but it is its own concept. It's a separate concept. And to understand what it is and why it's there, I think it's important to understand that while these numbers here in the prevalence ratio column look very definite, they are just estimates, ultimately. So for the people who conducted the study, the numbers they've given here in the prevalence ratio column are the best guess they have, but they are still a guess based on the data they have. Now, the confidence interval is showing a range of scores within which we can be 95% sure the true figure lies. So, in other words, for the 18 to 34-year-old group, the best guess we have for the prevalence ratio is 1.1, but we can be 95% sure that it's somewhere between 0.6 and 1.6. That's what this confidence interval is showing. Now, obviously, if you increase the sample size of the study, if you had a study with 7,000 people rather than 700, then you would be more confident of the result because you've got more people in the study. And then, as a result, the confidence interval would shrink. So it might go down to, say, 1 to 1.2 in this case. But for the present study with the present numbers, we've got the confidence intervals shown down here. The main thing is just to understand that it's a range of scores within which we can be 95% sure the true figure lies. With that in mind, let's go through the question and the answers. So which of the following can be concluded? Option A, So we're dealing now with the ethnicity subgroup, and we're saying that the Hispanic group purchased more medication than the non-Hispanic group. And that certainly seems to be the case. We can see that in terms of percentage, they're higher, 28% versus 17. And that's reflected, as you'd expect, in the prevalence ratio. We can see that our best guess is that the Hispanic population are 1.6 times more likely to purchase medication than the non-Hispanic group. But remember, that's just an estimate, and we need to look at our confidence interval to see how confident we are that that is the case. And here the range is 1.1 to 2.3. That means we're 95% sure the true figure is somewhere between those two numbers. And therefore, we can be 95% sure that the Hispanic population do purchase more medication than the non-Hispanic group, because this whole range, this whole 95% range, is above the number 1, which remember is the point at which the two groups are equal. So because this whole range, this 95% confidence range, is above that figure of 1, we can be sure, as the answer suggests, that there is at least a 95% chance that the prevalence of medication purchase in the Hispanic group is higher than the non-Hispanic group. And for that reason, option A is correct. If we quickly go through the remaining options, B may be tempting. Now remember, we're looking at the participants in the study, which is given by the subtotal group here. We're dealing with ages. So in this case, it may be tempting to go for it because you can see that these numbers in the percentage column add up roughly to 65%. But remember, that has nothing to do with the breakdown of ages. That's to do with the percentage of medication purchase. And actually, we can see that everyone in the study was above 18. So that's a lot more than just the 65% shown in option B, because everyone here was over 18. Option C, there were more Hispanic people included in the study than non-Hispanic. Again, it may be a tempting option given that a lot of the numbers here for Hispanic are higher, 98 versus 84, 28 versus 17, 1.6 versus 1. So a lot of higher numbers in the Hispanic row, but the key one, and the one we're interested in, is this column here, because ultimately it's a question of the number of people who are in the study in the Hispanic and non-Hispanic groups. And as you can see, the non-Hispanic group had more people. So option C is incorrect. And finally, the reference group was the largest group in each demographic category. Well, it seems to be in almost every case, except for this one here, the gender group, where you can see the reference group here is the male group, even though the subtotal number is lower than the female group. So there were more female participants in the study, but the reference group was still taken as the male group, and for that reason option D is incorrect. We'll just do another question based on the same table to reinforce the same concepts. So now the question is, which of the following can be concluded about medication purchasing in Mexico with respect to medical insurance? So we're dealing now with just the final few rows here, where we've got medical insurance and the various medical insurance subsections. Option A, those with full coverage were more likely to purchase medications than any other insurance group. This may seem tempting because if we go through the medical insurance groups here, the group with the highest number of people purchasing medications is the full coverage group. But remember, the wording of option A is the group which is more likely. So it's a function of the total number of people as well. It's a percentage, in other words, that we need to find. So really the column we're interested in is the second column here, which is showing the percentage of people in each subgroup who purchase medications, because that's the one which will show us who's more likely. And as you can see, actually the full coverage group are the least likely, because they've got 17 compared to 25, 30, and 45. So option A is not correct. Option B, those who were in the self-paid group made about a quarter of those, or made up about a quarter of those who purchased medications. So now we're looking back at that first column, because we're looking at the raw number of people in the self-paid group who purchased medication, which is 34, as we can see there. And the question, or the option, is saying that that number there is about a quarter of the total number of people who purchase medications. So we have to work out if 34 is about a quarter of the total number here, which is 183. And I would say that it's probably not, that 34 or 34 would be roughly a quarter of 140. So that's a bit off 183. There's a bit too much of a difference there to conclude B, at least at this stage. Option C, approximately 70% of people in the study had full coverage insurance. So now we're looking at the third column here. We're looking at the subtotal for each of the four groups here. For full coverage, we've got 545, and that's out of a total of 775 people in the whole study. And so we're being asked if that is roughly 70%. Is this group roughly 70% of the total group? And I would say it roughly is. Again, don't be afraid to round. You can round this up to 550 if it helps, or even up, or with the 775, you can round it down to 750 or up to 800. Either way, I think it's pretty close to 70%. Certainly closer than option B was. So at this stage, I think C is the best answer. And option D, there is at least a 95% chance that the prevalence of medication purchase in Mexico is higher in the self-pay than the full coverage group. So it's very similar to option A in the last question, which ended up being the correct answer. We're looking now at the self-pay and the full coverage group, which is the reference group. And even though it looks as though the self-pay group are more likely to purchase medication with a prevalence ratio of 1.5, you can see the reference group here includes 0.9, which, if that was the case, would mean that actually the self-pay group purchased less medication than the full coverage group because it's under or below 1. So we can't be 95% sure that the self-pay group purchased more medication because part of that reference group, part of that confidence interval group is below 1. So that can't be correct. And therefore, of the four options, I think the closest, particularly given the nice kind of general open-minded wording of approximately, would be option C. Question 8 now. This table looks a bit different to previous ones. You can see that we've now got cells containing just colors rather than numbers or words. The other confusing thing I think initially is that there is no real title up the top, or at least no title that gives us an overarching picture of what the table is about. So the best indication comes from down the bottom here, where it says 5-year cardiovascular risk, both fatal and non-fatal. So what that's telling us is that the table is showing us the risk people have of a cardiovascular event over the next 5 years. And you can see below we have a sort of key here where the different colors correspond to different groups or different ranges of risk. So how come there are so many different cells? Well, as you can see, there are multiple different variables at play here. On the left-hand side we have age, and you can see that each big box represents a different age range. Across the top we have smoking and non-smoking. So down this side are non-smokers and down this side are smokers. On the right hand side we have systolic blood pressure. So each row represents a different blood pressure group. And the bottom is BMI. So each of the smaller columns is a different BMI. And that means that every box, every small little rectangle in the table here represents a different combination of those four factors of age, smoking, blood pressure, and BMI. And the color inside that cell represents a different range of risk for 5-year cardiovascular events. So once we've got that clear, it's just a case of going through the options and reading carefully. So which of the following is not true? So already there's a trick. Which of the following is not true? So we're not looking for the correct answer, we're looking for the one which is incorrect. Option A, smoking non-diabetic men. So already it's a good start because it's mentioned non-diabetic men, which is what the table deals with. Smoking refers just to the right-hand side of the overall table. Age between 55 and 64. So now we're looking just at this square or this rectangle here. And it says that they can have a cardiovascular risk, or a 5-year cardiovascular risk, of anywhere from 10 to 100%. So that's pretty good. All the wording is pretty good. It's the same as down here, 5-year cardiovascular risk. And we want to work out what the range is for this square here. To do that, we have to look at the worst case and the best case scenario. So the best case is down here, this green box here, which according to the key represents a 10 to 20% chance of, or a 10 to 20% cardiovascular risk. The worst case is up the top here, which is red, and red represents over 40%. So in theory, this is correct because at the lowest, you could have a risk of 10%, as shown by the green, and at the highest it could be anywhere over 40, which could include 100. Now in practice it's very unlikely to be 100, but from the table we can only conclude that it's over 40. So that could be 100, and therefore A could be correct. And for that reason, it's not the correct answer, because we're looking for which of the following isn't true. So let's look at B. B gives us a pretty specific set of descriptions. So let's have a look. So 63-year-old non-smoking non-diabetic male, BMI 29, blood pressure 150. So non-diabetic male is good. That's what the table is looking at after all. If you look at the fact that he's a non-smoker, we're now looking just at the left-hand side. 63 years old, so we're looking just at this big square there. BMI 29, so just this row just here, or this column rather, and blood pressure 150, so we're looking at this cell here. So we're just referring to this particular cell. And as you can see from the key, that green color corresponds to a 10 to 20% risk. So the question is whether that person has a lower 5-year risk than a 45-year-old smoking non-diabetic male, BMI 25, blood pressure 172. So again, just track down that particular cell. 45-year-old smoking, so looking at smoking on the right-hand side. 45 is this square here. BMI 25, that's just here. And blood pressure of 172, so that's right up the top here, which is yellow, and yellow represents a 21 to 30% risk. So the first person had a 10 to 20% risk, and that is indeed lower than the second person who had a 21 to 30% risk. So B is an accurate statement, and therefore it's not the correct answer. If you look at C, a 60-year-old non-diabetic smoker with BMI of 28, I'm going to stop at this point because the issue already is that it just says non-diabetic smoker, but not a non-diabetic smoking male. Because there's no mention of the male, we can't really conclude anything about this particular option, because the table is just showing us men, not the whole population. So this is looking like a pretty good answer, given we're looking for which of the following is not true, because we can't conclude option C, given option C is referring to the whole population, whereas the table just shows men. If you put the word male in there, otherwise it looks pretty correct. If you find the cell which corresponds to the various variables, it'll be the right color and the right risk factor. But that's a pretty important detail. So this is the importance of careful reading and of making sure that every word you need is in the answer before you conclude it. Just finally, option D, a non-smoking non-diabetic man, age 40. So we're looking now at non-smokers, so left-hand side, and aged 40 is in this bottom square here. We'll have a 5-year cardiovascular risk of less than 10% regardless of BMI and blood pressure. Well, given the whole big square down here, which we're looking at is blue, which is less than 10%, that would be pretty accurate, because it doesn't matter what your BMI or what your blood pressure is, you're always going to be below 10% at that stage. So D is an accurate statement too. Given A, B, and D are accurate statements, and C just lacked that one word, male, I would say that the worst option here is probably C, and therefore given we're looking for which of the following isn't true, that would be the correct answer. So C. This question is again based on the same table, but we're now being asked which of the following people out of the 4 options could reduce their 5-year cardiovascular risk by the most by reducing their BMI and blood pressure to the lowest ranges shown in the table. So I think the easiest way to do this is just to highlight the 4 different cells in the table that relate to the 4 different people. And from there we can visualize who can drop their overall risk the most. So I'm going to get the pen out. And I'll just make it black so you can see it against the table. So if we look at option A, again the key words are there. We've got non-diabetic and man, so that is in keeping with what we have in the table. We're looking at a smoking person, so that's the right-hand side. 70 years old, that's the top square here. And BMI of 24, so this column here. And blood pressure 130, so looking at this cell here. So I'm just going to write in A, just to say that this is where option A, or the person described in option A, is currently sitting. B, same process, so non-smoking, looking at the left-hand side, 65-year-old, again, top square here. BMI 31, blood pressure 165. That would be this square here. So I'll put a B in there. Oop, that's a B, believe it or not. C, smoker, right hand side, 60 years old, this square here. BMI 26, blood pressure 150. So we're looking now at that square there. So I'm just going to put a C in there. And finally, smoker 54. So looking at right hand side, 54 is this square here. BMI 35, so the final column, and blood pressure 180. So we'll put a D in there as well. So these are where the 4 people currently sit. And the question is asking who can reduce their risk the most by lowering their blood pressure and their BMI to the lowest ranges shown in the table. So we can't change their age, obviously, and we can't change their smoking status because that's not mentioned here in the question. So the box that they're currently in is where they'll stay. In other words, B will remain in this top left box regardless of how you change their blood pressure and their BMI. But if we reduce the BMI and the blood pressure to the lowest point possible, shown in the table, that would be the bottom left box. So if you imagine, say, with person A, that we drop the blood pressure from 130 down to the lowest point, 111, and we drop the BMI from 24 to down here to 15 to 20, then that would be their new position. They would move from this box down to the very bottom left here. Likewise for B, they would just move down to the bottom left here, C would move to there, and D to there. So we just have to work out which of those is the biggest drop. Well, with A, they actually haven't changed the category they're in, so the change there is negligible. With B, they've gone from the red box up here to the green. So that could be anywhere from above 40 down to 10 to 20, which is pretty significant. C has gone from 31 to 40 to, again, green, 10 to 20, and D has gone from yellow to green. So the biggest change out of that is B, because out of B, C, and D, they all end up in the green, in the 10 to 20% risk category. But D started in the yellow category, C in the sort of orangey brown, and B in the red. So out of those, the biggest change is B. Therefore, person B could stand to reduce their risk the most by dropping their blood pressure and BMI. So that is the correct answer. Final question now. It's pretty straightforward, but again, it's a little bit different in terms of style. So I've just run it in so you can appreciate the range of different tables you can get. So let's read the information here. You can see that the above table is a timetable for a number of doctors across 2 practices, practice A and practice B. And the question is how many doctors are working at either practice at 1:30 on Monday? So again, 2 practices, A and B, and each row represents a different doctor across the various days of the week. And the color coding is given here in the key. So each color represents a different time period that each doctor is working on each day at the different practices. So we're looking for how many doctors are working at 1:30. So I think the first step is just to work out which colors include that time of 1:30. So not white. We can see white finishes at 1:30. Sorry, at 1 o'clock, which is before 1:30. The 2 grays include 1:30, and the black one here doesn't because it starts at 2. So the 2 grays are the ones we're interested in. They're the ones which contain 1:30 p.m. So all we have to do is go down the Monday column for both practice A and practice B and count up the number of grey shadings we see, and that total will be the number of doctors working between the 2 practices at that time on that day. So practice A, we've got 1 here, 2 there, and 3 at the bottom. Practice B, we've got 4 and 5, so a total of 5, which means that the answer would just be A. So pretty straightforward, but again, a bit of a different style. And it's just good to see it before the exam and to have a good appreciation of all the different styles that you've seen in this video. But basically it comes down to careful reading of the tables and particularly careful reading of all the answers and making sure that all the technicalities and the various words you need are included in the answer you ultimately go for. So yeah, that's it for this video. Hope it helped.